Alright, let's talk about bimolecular nucleophilic substitution reactions, also known as Sn2 reactions. You may remember from general chemistry that when a reaction goes from the reactant side to the product side, and in this case assuming it's exothermic, you have an energy profile for the reaction as follows. This is known as a reaction coordination or a reaction coordinate diagram. And the parts that are important for our discussion are the energy location of the reactants, the energy location of the products, and the activation energy. Now, at the activation energy, that is the top portion of the energy profile of the reaction, right? This is the energy required to get the reaction going. You have something known as a transition state. And the transition state is the look of the molecule or molecules as the reaction is progressing forward. And it's not exactly a molecule they can isolate. It is what's hypothesized to happen in the course of making the products and corroborates very well with experimental data, but we have no real proof that that's what happens. It just so happens that it explains things very well based on the data that we have. Now, the activation energy determines the kinetics of the reaction, whereas the changing energy of products, from reactants to products is the thermodynamics, your delta H, etc. But let's take a look at the kinetics. You may recall that the rate of a reaction is given by the negative rate constant times the concentration of the reactant raised to some order. And the order could be 0, it could be first order or second order, and that really tells you just what the exponent is going to be here. This look at the kinetics also was investigated using the Arrhenius equation, which is presented right here, that allows you to determine the activation energy of the reaction. But there is another equation known as the Eyring-Polanyi equation. This one you may not have seen in the past. This one is an equation that ultimately tells you the story at the transition state. And the two things to notice is that you have an enthalpy term as well as an entropy term, but they all have this double dagger symbol. And what that symbol represents is that you are looking at the transition state. So this is the enthalpy of the transition state, and this is the entropy of the transition state. So when someone does a reaction, like an Sn2 reaction, where you have two reactants, what we find out is that both reactants play a role in the kinetics of the reaction. So the rate law is given by negative K times the concentration of reactant 1 times the concentration of reactant 2, both to the first power. But collectively, this is a bimolecular reaction. The other experimental observation is that the delta S double dagger term is negative in an Sn2 reaction. And since this is an entropy term, if the entropy is negative or the changing entropy is negative, what this is telling you is that the entropy is decreasing as the reaction is progressing forward. And decreasing the entropy is the same thing as saying that you are creating a more ordered transition state. And for you to have a more ordered transition state and undergo this process of exchanging the nucleophile Y minus with the leaving group, or excuse me, the leaving group with the nucleophile, the only way you can make those two things happen in the course of this reaction at the transition state is if the nucleophile partially begins to form a bond with that electrophilic carbon and the leaving group partially begins to break the bond that it has to the very same electrophilic carbon. Now, in essence, this forms this pseudo trigonal bipyramidal transition state, which sure enough, when you compare this transition state to the individual reactants that are free to go whichever way they want in this state, this is a much more ordered molecular shape. Therefore, your entropy is going to decrease. Now, as the reaction continues to go forward, the carbon bond to the leaving group breaks up entirely and the leaving group takes off, and the bond to the nucleophile is finalized and fully formed. The other thing too is notice that here we have an umbrella pointing to the left, but by the time Y has come in, it's turned that umbrella into a flat trigonal planar shape, which once the living group takes off, the umbrella now goes in the opposite direction. This has a major outcome. First of all, the attack will always happen opposite to the living group so that you can enact this type of transition state. And what this ultimately means is that you are going to invert the configuration of this carbon, meaning that if the carbon was chiral to begin with, let's say that it had the R configuration, by the time you're finished with an Sn2 reaction, the chirality could become the S configuration. Ultimately, it really depends on the identity of Y, because the RNS assignment depends on the priorities of all these groups. So it's not always going to be the case that if this is R, that becomes S. It kind of depends on which groups you are putting onto the electrophilic carbon and what groups you had to begin with. In some cases, yes, exactly this is going to happen. R becomes S. All right, now the second aspect of Sn2 reactions that is important to point out is that because we are emphasizing the idea that a more ordered transition state is going to occur in which both the living group and the nucleophile are present in the same molecule at that point in time with partial bonds, this creates a problem. In the case of methyl groups, well, the hydrogens don't really take up much of a space, so this doesn't look like that bad of a scenario. So, typically you'll see this and this is fine. You could definitely make that happen. But what happens when you start introducing substitutions at the electrophilic carbon? What if instead of a methyl group you have a primary electrophilic carbon? Well, you will still have to go through this transition state, but now you have that carbon sticking out there, which kind of partly begins to, repulsively interact with the living group and the nucleophile. All right, so that's not as good as the methyl strategy, but still not too bad. You can still make this happen. But introduce a secondary carbon, and now here's where things get funky, because the process now has enough steric bulk around the electrophilic carbon that the nucleophile may have a hard time reaching onto the electrophilic carbon. Therefore, in some instances, you are going to get the reaction to go forward, and in other instances, the reaction will not go forward. And we're going to talk about the conditions that will dictate whether secondary alkyl halides or electrophilic substrates undergo Sn2 reactions with secondary electrophiles and when they don't. Now, the final case, you might have guessed it, tertiary alkyl halides. In this case, you have so much steric bulk because you have 3 R groups present in here that the nucleophile trying to reach over opposite of where the living group is located is almost impossible. In fact, it's so bad of a repulsive interaction that this rarely ever happens. Technically speaking, it doesn't happen. And so Sn2 reactions are really seldom seen with tertiary alkyl halide substituents. And it's important to keep that in mind because we are going to ultimately use that information to determine whether a reaction is likely to go by the bimolecular nucleophilic substitution mechanism known as Sn2. All right, let's see what happens with a unimolecular nucleophilic substitution. In a unimolecular nucleophilic substitution known as Sn1, only one out of the 2 reactants is involved in the rate law of the reaction. And not only that, but the delta S double dagger term is positive. And what this means is that the changing entropy is increasing. And if the entropy is increasing, you are getting a more disordered state from what you started with. So if only one substrate is getting involved in the kinetics of the reaction, and you're forming a state that is more disordered, one way to make that happen is to start with a substrate that has the weak carbon X bond to be broken heterolytically, and simply break the bond. literally remove that leaving group, have it take off. And when it takes off, you form what we call a carbocation. The carbocation is trigonal planar in shape, but what you will notice is that you started with only one substrate or one molecule, and on the product side you have two different products, the anion and the cation. Therefore, you have increased the entropy. So this explains, that idea of having only one of the molecules interacting in the rate law of the reaction and increasing the entropy at the transition state. Now, of course, the carbocation intermediate is not the final point of the substitution reaction. You still have to substitute X with something. And so the moment the carbocation is formed, the nucleophile now can finally come in and attack. And the reason the nucleophile wasn't reaching over before is because you had too much bulk around the electrophilic carbon. It couldn't really reach over, so you had to wait until something was gone for it to actually be able to react. But once that leaving group takes off, you have now enough room to make this happen. Nucleophile attacks the electrophilic carbon and you form your product. All right, but unlike Sn2 reactions, because you are forming this carbocation intermediate, which is trigonal planar in shape, you really have two choices. You could attack with your nucleophile from the top face of this trigonal planar molecule, or you could attack from the bottom. There's actually no energy distinction between these two attacks. So what ends up happening is that on the one hand, you get the umbrella to open down, yielding the following product, or you get the umbrella to open up, yielding the product right here. And so if your molecule had three different groups and the incoming nucleophile is yet a different group from the original three, you are creating a chiral substance, but the chiral substance is basically producing both enantiomers. It's producing the R enantiomer and the S enantiomer as a result of being able to attack from both the top and the bottom face of the trigonal planar intermediate. So when you get a solution of this kind, the molecule is chiral, but you have no optical activity whatsoever because you have 50-50% of the R and S enantiomers. And whenever you have a 50-50 mixture, your percent enantiomeric excess is equal to 0. And when your enantiomeric excess is equal to 0, your optical activity is also 0. All right, now the last thing is just to show you about the stability of the carbocations. And this is very similar to what we mentioned about radicals. You have your trigonal planar shape, and to have a carbocationic carbon is to say that you have an empty p orbital with no electrons. This is an electron deficient center, one that doesn't have the full octet. It doesn't violate the octet rule in the sense that you have more electrons than you could possibly occupy. You have less. That's not good, but it is allowed. Now, what happens is that when you look at the methyl group, there's really no stability whatsoever there, but start substituting the carbon, with an alkyl group or two alkyl groups or three alkyl groups. In other words, go from methyl to primary to secondary or tertiary carbocations. And what you basically have is this picture of the neighboring alkyl CH bonds making themselves parallel to the empty p orbital. And since the bonds have electrons, you can actually, by proxy, stabilize this empty orbital, and we call this hyperconjugation. Now notice that for the secondary and the tertiary carbocations, you get the most hyperconjugation onto that empty p orbital, and as such, tertiary carbocations are the most stable of the bunch, followed by secondary. Primary doesn't get enough to really facilitate the formation of the carbocation, and methyl doesn't even have these alkyls, neighboring the carbocation, so it doesn't even get hyperconjugation. So what you're going to see is that when it comes down to Sn1 reactions, this only really happens with secondary and tertiary alkyl halides. Okay, in the next video, we're going to talk about the factors that do favor Sn2 reactions and those that favor Sn1 reactions. So see you in the next video.